Hello, everyone. My name is Navid Zoberi, and I'm an assistant professor at the University of Washington. My areas of impact are aerospace and advanced manufacturing, especially by leveraging automation and AI. Fun facts about me is that my first spoken word was hot. It was a very fitting start for me because I love cooking. I even published a cookbook with my wife and my mother and my mother-in-law. And in my everyday professional life, I use principles of heat transfer. I also have another thing in common with our second speaker. I also watch Korean drama with my wife, so that's the other thing. Yeah. Okay, so I graduated from University of British Columbia, UBC, in Vancouver, Canada, 2.5 hours north of here in 2010. Then I worked as a postdoc for 2 years. During that time, I contributed to establish a national research center in Canada, focusing on manufacturing. Once the center started in 2012, I transitioned to that center. I worked in that center for 7 years as a lead scientist. I also was a lecturer at UBC during that time. So during that time, I worked with more than 150 companies, helping them with different manufacturing problems they had. And these are companies, big companies, in aerospace, for example, Boeing and Bombardier, to automotive like Honda and Ford, all the way to small bike shops and boat manufacturers, even companies who were making rides for Disney. So I helped quite a few companies, and when I moved to UW in 2019 as an assistant professor, I focused in aerospace. For two main reasons. First of all, proximity to aerospace industries in Puget Sounds, and I have a very close relationship with Boeing, but also other companies like Lockheed Martin, Air Force and NASA, and so on and so forth. Also because of my own interest in aerospace. So I'll share with you the very first project that we did at UW with 3 of my master's students. And we started this project months after I arrived here. I'm going to show you how I combine my passion of cooking with my professional life. So this is a very common scene in aerospace. On the left is a giant autoclave, which is basically a pressure cooker. And you cook multiple aerospace parts together inside this autoclave. And once they're cooked, you will assemble them and go to the next step. This is equivalent of, let's say you're doing Thanksgiving dinner, and guests are coming. You have 2-3 hours. You have to cook a turkey, multiple pizzas, lasagnas, desserts, roasted vegetables, all in your tiny oven. And you don't have time to babysit this process. You just have to go and talk to your guest. So you want to load up your oven and leave. So this is the exact same dilemma that guy has in an aerospace factory. So we thought about this and thought, wouldn't it be better if the autoclave, and in that case, oven, could make decisions on its own? It becomes a smarter oven. And this is exactly what we did. So this is a patented process at the moment. I'll explain to you how this works. Basically, inside the autoclave, there are many parts that you're cooking. There are lots of thermocouples or thermometers, one for each part, that are measuring the temperature. And they are fed into a data acquisition system. And then the data is being analyzed by a trained AI. And the AI does 2 things. First of all, it predicts what's going to happen to these parts 1 hour, 2 hours into the cooking. Based on that knowledge, in real time, it optimizes the temperature of the autoclave, communicates it back with the autoclave controller, automatically adjusted. And it goes into this loop that's optimized. And at the end, it ensures that all the parts are cooked to the same level of perfection at minimum time required. So you can go to the next load. So this is where I'm going to stop. My book is available on Amazon if you want to buy it. Hey. So what is material science and engineering? And I'm going to show it to you with 2 simple examples. One is making chocolate, the other one is making airplane. And UW newspaper is going to publish this in Valentine in 2 months. So if you are interested to learn more about this, you can read in the newspaper in 2 months. But you've probably seen chocolatiers that they take melted chocolate, they spread it on a marble surface, and they slowly play with it, spread it. What they're doing actually, they're controlling how fast the chocolate is cooled down. They're controlling the cooling rate of the chocolate. If you're precisely controlling the cooling of the chocolate, it results in a very special crystal morphology in the cocoa butter. And that's the secret trick. That's the trick of how to make good chocolate. If you are successful in making that microstructure, the end chocolate has some very desirable properties. It will have a reflective surface. When you snap it, it will have a satisfactory sound, and it has a very precise melting temperature, 1 degree below our body temperature. So when you put the chocolate in your mouth and you close your mouth and you wait, it resists and then it slowly melts away, and that adds to the luxurious experience of eating chocolate. And all of that are by design. So we call this the tetrahedral of material science and engineering. Process, structure, properties, and performance. And this is so important to discover this that we name human eras after this, like Stone Age, Iron Age, Bronze Age. These are all eras that we mastered this tetrahedral for one material. So I'm going to go now to a comparison of how we make aircrafts. To make aircrafts, at the moment, we are trying to use a very specific material called thermoplastic composite. These are plastics reinforced with carbon fiber. The process is that using robotic arms, which we have a similar one at UW, fortunately, we can place the material onto a mold. During that time, you are melting the material with laser. If you can control the cooling rate of the material, it results in a very special microstructure. You can see the crystals forming around the fiber. And if you're successful in developing that microstructure, it will give its very high properties, high strength, thermal durability, chemical durability, and that results in aviation, the performance at the end. So this tetrahedral is the same thing. So the whole material science engineering is around this very powerful concept. Once you master this concept, what type of jobs you can do? I mentioned aerospace, composite manufacturing in aerospace. Most of the people that I know they have very strong background in material science and engineering. If you look at the space exploration, the heat shields are typically developed by material science and engineers. In fact, MSc department in this university built its name in 80s and 90s by developing the heat shield for space shuttle. Advanced manufacturing, if you think about additive manufacturing of metals, you have to understand that tetrahedral. If you think about electronics and semiconductors and chip manufacturing, almost half of the faculty members in my department are expert in that field. It's a very strong field of material science engineers. Energy application, developing new batteries, that's also beyond the chemistry. Beyond that, you have to master that tetrahedral. And biomaterials. Even R&D labs developing new materials, advanced materials. The Gorilla Glass on your cell phone is developed by material scientists in Owens and Corning. Specialty coating is the other area. I have 2 master's students that just graduated now. They're joining Boeing to develop specialty coatings for Boeing. I'm going to end this with a quote, with a tweet from Elon Musk. It says, "Take material science 101, you won't regret it." Okay? If you're interested to learn more about my departments, there's some QR codes.